This video is going to go over intermolecular forces and the three main forces that we talk about in this category. So inter means between like molecules, So want you to think of a beaker of water. So draw yourself a beaker of water. And this beaker of water is held together, okay, by some kind of forces. So I want you to think of phase changes as a way to kind of understand these intermolecular forces. Now we talked about it in thermo, that there was energy going into changing something from a solid to a liquid or a liquid to a gas. So we just never discussed what that energy, we talked about how it was spreading out the particles or bringing the particles together, but it was really these intermolecular forces that were keeping those particles as such. Intramolecular forces are the forces within the molecule, So those are the bonds. So that's what we just covered in the last unit. So this would be ionic bonds, this would be covalent bonds, this would be metallic bonds. Okay, so it's within the molecule itself. So if we use water as our example here, it's the bond that is between the hydrogen and the oxygen. That's an intramolecular force. Now, these forces do influence the outermost force or the forces between the molecules, but these are something we've already discussed. This is the micro scale, meaning we're talking one molecule at a time, while this is more of the macro scale. So this is a billions upon billions of water molecules in a beaker. So that's the difference between the two. So intermolecular forces are the weakest forces in a molecule or compound. So there are three different kinds of forces that I'm going to talk about: dispersion forces, dipole interactions, and hydrogen bonding. And understand on this list, the weakest of them all is the dispersion forces, and the strongest is going to be the hydrogen bonding, okay, in relation to each other. So it's not going to be looked at according to ionic or metallics. Again, covalents are usually what we're dealing with intermolecular forces, but just so you know the distinction between the two. So I'm going to talk about each one of them individually, Okay, so dispersion forces are the weakest forces caused by what we call the movement of electrons. So when we draw molecules, like let's say a molecule of F2, and we draw these shared electrons between the two, these electrons are constantly moving. And so when we draw them on a piece of paper, it's sometimes lost in translation exactly what is taking place here. But dispersion forces is kind of the catch-all for the fact that everything has electrons. And so since everything has electrons, there's some kind of force that keeps everything together. That's because the electrons move. Maybe the electrons are both on one side versus the other side of the bond, which causes what we call a temporary, positive and negative end. And so there's some attractive forces that keep them together. The way to kind of explain dispersion forces is as follows. So halogens, if you look them up on the periodic table, they have different states of matter depending upon who they are. So fluorine and chlorine are both gases at 25 degrees Celsius. Bromine is a liquid and iodine is a solid. Now that makes no sense because they're all halogens. They all want one electron. They all are diatomics. They react very nicely with metals, all sorts of similarities, but their states of matter at 25 degrees Celsius, again at 25 degrees Celsius, they all are different. Why? Okay, so the rationale or the theory behind it is called dispersion forces. Molecules with higher molar masses will always have more dispersion forces. So the more mass you have, the more electrons you're going to have. So the more electrons you have, the more chances you have for what we call dispersion forces to be. But please remember that everything has dispersion forces. So it is the weakest force, but every molecule has it. So that's how fluorine and chlorine kind of stay together when they're a gas, and bromine sticks together even more, and iodine sticks together the most because you have the most electrons in that group. So second one is called dipole interaction. And this one actually, out of all of the ones that I'm going to discuss, is probably the easiest one to understand. It is between what we call polar molecules. Okay, so something being polar is going to be important for your decision. So polarity just means you have a positive side and a negative side to the molecule. So I want you to think of a bar magnet with a north side and a south side, and kind of how they can't, north and north can't go together and south can't go together. So the same thing goes for a polar molecule. So if I use HCl as my example, and I'm using it just because it's nice and simple and small and easy for us to draw. So if I have a beaker of HCl and it is a liquid at room temperature, chlorine is more electronegative than hydrogen. So I'm going to use a dipole arrow. Anytime I could draw a dipole arrow means I have a dipole interaction, okay? So remember, the dipole is always pointing towards the one that is more electronegative. So that means chlorine is slightly negative and hydrogen is slightly positive. You don't need to know that these are lowercase deltas. They're just partial charges. And remember, again, this is a plus sign on the dipole arrow. So if I have a north side and a south side, how will a neighboring HCl molecule orient itself? Well, the H would come over here and the C will go over here, and then another molecule would go like this. So you would have a repeating pattern back and forth with the positive and the negative end kind of lining themselves up, because two negatives together will repel, two positives together will repel. So this is how HCl would kind of organize itself in that liquid, so that you would see every other one would be kind of essentially flipped, because the hydrogen end is positive and the chlorine end is slightly negative. Okay, so dipole, again, happens with polar molecules, So pretty straightforward. So the last one is probably the trickiest of them all. It's called hydrogen bonding. And this one is always confusing to students because it really should be called hydrogen force. It's not a bond, but it's a very, very strong force compared to everything else that we have in intermolecular forces. So hydrogen bonded to highly electronegative elements. So it's only when hydrogen is bound to fluorine, nitrogen, or oxygen. So I'm going to give you an example of each. So hydrogen attached to fluorine, so HF is a formula. Nitrogen attached to hydrogen, so ammonia, NH3. And then, of course, our friend water. And that's going to be the one that we talk about the most, is water, okay? So water has hydrogen bonding, and it lends itself to a lot of interesting properties that that water has that other molecules don't have. Okay. So if I draw a water molecule, and give yourself a little space on this, with two lone pairs, okay. If you did the reading, you will know that oxygen is more electronegative than the hydrogen. You will see dipole arrows pointing along the bonds between the hydrogen and the oxygen. So you have dipole arrows pointing that way. Since you have two of them and they don't cancel out, you have a polar molecule. So sometimes you will see an overall dipole arrow drawn through the whole molecule to show that this side is positive. So this side is positive and this side is negative, because all of the electrons are being pulled towards the oxygen because of their electronegativity. So if this is a water molecule, the red being the oxygen and hydrogens being the white, if I have a neighboring water molecule, okay, it's going to orient itself according to positives and negatives. So see how the oxygen attached to the hydrogen end of this water molecule. And if I put another one, it will do exactly the same thing. Okay, so what you have is a positive and negative end of this molecule. So this is a more pronounced dipole as a way to think about it. So please draw another water molecule next to this water molecule, but have the oxygen pointing towards the hydrogen end of this one, and put a dotted line between the two. Most books write it as a dotted line. This is the hydrogen bond, or hydrogen bonding. Again, it should be called hydrogen force, but unfortunately, that's what it is. So it's not the bond between the oxygen and the hydrogen. It is the bond between the two adjacent water molecules, so next door neighbors, okay? So one water molecule by itself When you start to put another one there, it will attach with the hydrogen to the oxygen end because one is positive, one is negative. So this repeats over and over and over again. So again, you could draw another water molecule with oxygen pointing towards that hydrogen. And it's that dotted line. This is the hydrogen bonding, which you could abbreviate as H-bonding for it. But again, it's always the oxygen end pointing towards the hydrogen end of the adjacent molecule because there's that attractive force that pulls them in, So what are you going to do with this? Well, you're going to determine which one has the higher boiling point. That's going to be the stronger force. So this is similar to ionic bonds and the fact Coulombic charge. The Coulombic charge is bigger, the melting point is going to be higher. The reason this is a boiling point is because typically these are liquids or gases. So that is why we have them as boiling points. So for these comparisons, I'm always going to encourage you to draw the molecule so you could see what it is, and then explain which one has the higher boiling point. So understand that Cl2 and HCl both have dispersion forces because everything's always going to have dispersion forces. But what you have to look at, does it have anything besides dispersion? So Cl2 is a non-polar molecule, okay? They are both the same thing, so they're going to be non-polar. HCl is going to be polar because the chlorine has a higher electronegativity than the hydrogen. So because I could draw a dipole arrow, it has dipole forces. And if it has dipole forces, it's going to have a higher boiling point. All right, so why don't you stop the video here and see if you could draw C2 and H6 and then C4H10 and see which one you think is going to be the higher boiling point. So pause the video and see if you could figure it out. All right, so both of these molecules are nonpolar. Okay. They both have dispersion, but I'm never going to give you a question that they both have the same boiling point. That's not possible. So the reason C4H10 has a higher boiling point is because it has a higher molar mass. There are more carbons and more hydrogens there. So therefore I have more electrons. If I have more electrons, I'm going to have more dispersion forces than the C2H6. So therefore my boiling point is going to be higher. My boiling point is going to be higher. So in conjunction with that, okay, C2H5OH, another molecule, okay, another molecule, C2H5OH, 2 carbons attached, and then I'm going to put 3 hydrogens here and 2 hydrogens here, and then an oxygen and a hydrogen there, okay? This is called an alcohol group, an OH group, okay? That's why it's separated out. The hydrogen isn't with this hydrogen here. So please recognize that this part of the molecule is going to be nonpolar, but because I have the oxygen pulling on those electrons more than the carbon is, this is going to make this molecule polar. Okay, so I have some dipole forces besides dispersion, but recognize that since the hydrogen is directly attached to that oxygen, this is actually hydrogen bonding. That's going to be the strongest force in here. So yes, it has dipole, and yes, it has dispersion, but the strongest force you have here is the hydrogen bonding. So anytime hydrogen is directly attached to oxygen, fluorine, or nitrogen in a molecule, you're going to have hydrogen bonding. So this would have the highest melting point, boiling point between the 3 of them. Okay, so I just wanted to show you that example for your notes.